And due to their simple operation and reliability, diodes are widely used in rectifiers and freewheeling circuits. The slide then discusses thyristors or silicon control rectifiers, or SCR in summary, which are control unidirectional switches. And SCR turns on when a gate pulse is applied and continues conducting even after the gate signal is removed, providing that the anode current remains above the holding current value. SCRs are commonly used in control rectifiers and AC voltage regulation systems. Finally, the slide explained transistor-based power switches, including the bipolar junction transistor (BJT), metal oxide semiconductor field effect transistor or MOSFET, and the isolated gate bipolar transistor (IGBT). The BJT operates as a current control device, while the MOSFET is a voltage control and offers very high switching speed. The IGBT combines the easy gate control of the MOSFET with a high current capability of the BJT, making it highly suitable for high power applications. These transistor devices are extensively used in inverters, DC choppers, motor drives, and high frequency power converters. Okay, this slide introduce uncontrolled signal, single phase and three phase AC to DC converters, commonly known as rectifiers, which are used to convert AC from the electrical grid into a fixed DC output voltage. These converters are called uncontrolled because they use only diodes as switching devices, and the conduction of the diodes occurs automatically according to the polarity of the input AC voltage without requiring any external control or gate signals. As a result, the output DC voltage is fixed and cannot be actively adjusted by the user. So the slide highlights that the simplicity, reliability, and low cost of diode rectifiers make them widely used in many industrial and commercial applications. Typical applications include DC power supplies for electronic equipment, battery charging systems, and front-end rectifiers stages in motor drives, and inverter systems are some of the examples that can be widely used in real-world applications. In addition, uncontrolled rectifiers are also employed in electrolysis and electroplating process where a stable DC supply is required. This topic forms the foundation for understanding more advanced control rectifiers systems used in modern power electronics. Okay, single phase and three phase rectifiers are essential circuits for converting AC voltage into DC voltage, and their design greatly affects the quality of output. The single phase half-wave rectifier is the simplest form, consisting of just one diode. During the positive half of the AC cycle, the diode conducts and passes current to the load, while during the negative half, it blocks the current. As a result, the output is a pulsating DC that has very high ripple content because of its poor efficiency and the heavy filtering required to smooth the voltage. This type of rectifier is rarely used in modern high power applications. A significant improvement comes with the single phase full wave rectifier, often implemented using a four diode bridge circuit. In this design, both half of AC waveform contribute to the DC output. This doubles the frequency of the output ripple compared to the half wave circuit, making it easier to filter and resulting in a smoother DC voltage. So These rectifiers are commonly found in low and medium power electronic devices such as chargers, small appliances, and consumer electronics. So for applications demanding higher power and improved performance, the three-phase full-wave rectifier is widely used, and this circuit employs six diodes arranged in a bridge configuration, ensuring that at any instant current flows through two diodes connected to different phases. So the result is a DC output that has very low ripple, is more continues, and closely resembles constant DC voltage. This small output reduces the need for bulky filtering components and increase efficiency. Because of these advantages, three-phase rectifiers are the preferred choice in industrial systems, motor drives, HVDC transmission, and other high power applications where stable DC supply is critical. Okay, when uncontrolled rectifiers are connected to an AC supply, the current they draw is not purely sinusoidal, so instead it is pulsating in nature because the diodes conduct only during certain parts of the AC cycle. This non-sinusoidal current can be mathematically expressed as a combination of a fundamental sinusoidal component at the supply frequency and several higher order frequency components which are known as harmonics. So harmonics are a significant concern in power system because they can lead to multiple negative effects. First, they cause voltage distortion across the network, which reduces the overall power quality. Second, they increase losses and overheating in electrical equipment such as transformers and motors, reducing their lifespan and efficiency. Finally, harmonics can produce electromagnetic interference that disrupts sensitive equipment and communication lines. So to mitigate these issues, you need to employ different harmonic reduction techniques. Passive filters are a traditional solution that use combinations of inductors and capacitors tuned to specific harmonic frequencies to observe and suppress unwanted components from the system. So more advanced approaches involve active filters, which rely on power electronic circuits that detect the harmonic content in real time and inject equal but opposite currents to cancel them out. So active filters are more flexible and effective across a wide range of conditions. Through they are typically more costly and complex compared to passive solutions. So in addition to basic harmony mitigation methods, one widely used techniques in high power applications is the use of multi pulse rectifiers. By combining multiple rectifier bridges with especially designed phase shifting transformers, low order harmonics such as the fifths and sevenths can be effectively cancelled out. So for example, 12 pulse rectifier consists of two 6 pulse rectifiers supplied by transformer windings that are pulse shifted by 30 degree. The resulting DC output is smaller and the harmonic content drawn from the AC supply is significantly reduced. So this makes multi-phase pulse rectifiers highly suitable for industrial systems and HVDC transmission where both efficiency and power quality are critical. Another important aspects of power quality in rectifiers is their sensitivity to voltage sags and soils. A voltage sag refers to short duration reduction in the supply voltage, while a voltage swell is a short duration increase. So since rectifiers directly convert AC voltage into DC, any disturbance on the AC side is reflected in the DC output. This means that voltage sags lead to a drop in the DC voltage, which can cause malfunction or even shutdown of the connected load. Similarly, voltage soils rise the DC voltage, potentially overstressing sensitive components. Severe sags in particular may cause the rectifier to stop conducting properly, interrupting the power supply to downstream systems. Therefore, understanding and mitigating the effect of the sags and soils is essential for ensuring stable operation in practical application. This slide discusses the analytical of single-phase full-wave uncontrolled bridge rectifier supply from 230 volt, 50 hertz AC source, a source with a purely resistive load of 50 ohm. In this configuration, the AC input is fully rectified using 4 diodes, producing an output waveform that is the absolute value of the sinusoidal input. The peak input voltage is first determined as Vm is equal to square 2 times 230, which is equal to 335 volt. For an ideal full wave bridge rectifiers, the average DC output voltage is given by VDC is equal to 2 V RMS over P, which resulted in approximately 207 volt. Since the load is purely resistive, the average load current can be directly calculated using Ohm's law. IDC is equal to VDC over R, yielding approximately 4.14 amp. So this example clearly demonstrates how full wave rectification improves the DC output level compared to half-wave rectification, making it more efficient for power conversion applications. This is a solution of this the previous example. Step by step, I explained that how you can use the formulation and everything. You can get a final result. Okay, this slide provide an overview of control and semi-control signal three-phase converters, also known as rectifiers. Unlike their uncontrolled counterparts, which use only diodes, these converters use thyristor SCR, giving them the ability to actively control the DC output voltage. So first, let me start to explain about control converters. A fully controlled converter uses only thyristors in its bridge configuration. This allows for complex control over the output voltage and critically enables bidirectional power flow. By controlling the firing angle or alpha, the average DC output voltage can be adjusted from a maximum positive value down to a negative value. When the output voltage is positive, the converter operates as a rectifier, converting AC power to DC. When the firing angle is delayed to be greater than 90 degrees, the output voltage becomes negative, allowing the converter to operate as an inverter. So sending power back from the DC side to the AC sources. So this bidirectional capability is essential for applications like DC motors drives with regenerating braking. Another converter is semi-controlled converter. So a semi-controlled converter or half-controlled converter uses a combination of thyristors and diodes. For a single-phase bridge, 2 thyristors and 2 diodes are used, while a three-phase bridge uses three thyristors and three diodes. This configuration reduces the number of expensive and complex to control thyristors. However, the presence of the uncontrolled diodes limits the converter's functionality. So the output voltage can only be controlled in a positive range from 0 to a positive maximum. The diodes prevent the average output voltage from ever becoming negative, which means the converter cannot operate as an inverter. The main advantages are lower cost and simpler control, making them suitable for applications that only require rectification, such as non-regenerating motor drives or battery chargers and so on. So the key principle here is that the fundamental principle behind all control rectifiers is phase angle control or firing angle or alpha control. The firing angle is the delay in degrees between the natural communication point where a diode would turn on and the point at which the gate pulse is applied to the thyristor. By increasing the firing angle, the conduction period of the thyristor is delayed, which reduces the average DC output voltage. This allows for continuous and smooth adjustment of the DC output from maximum at alpha is equal to 0 degree to 0 at alpha is equal to 90 degree for a fully controlled converter with a resistive load. This slide explains the major applications and operating modes of control power electron converters with particular emphasis on four quadrant operation. In rectifier mode, the converter transforms AC power into a controllable DC output voltage, making it highly suitable for applications such as DC motor drives, battery charging systems, and industrial DC power supplies where adjustable voltage control is required. This slide also introduces inverter mode where control converters operate with a firing angle greater than 90 degrees. Under this condition, power flows from the DC side back to the AC system, allowing the converter to function as an inverter. This operating principle is widely used in HVDC transmission systems and regenerative braking applications in motor drives where recover energy can be returned to the power source. In industrial motor drive systems, these converters provide accurate speed and torque control, improving efficiency and process performances. So this slide further highlight the importance of control converters in renewable energy applications, particularly in wind energy systems where they are used to connect and regulate the AC output of wind turbines with the electrical grid. Overall, this slide demonstrates the versatility and significance of control converters in modern industrial and power system applications. Okay, this slide discusses the concept of four quadrant operation in fully controlled rectifiers, which is one of the most important features of control power electron converters. Four quadrant operation means that the converter can operate in all regions of the voltage current plan, allowing bidirectional control of both voltage polarity and power flow direction. In quadrant 1, the converter operates in rectification mode where power flows from the AC source to the DC load with positive voltage and current. In quadrant 2, the converter operates in inversion mode, transferring power from the DC side back to the AC systems. Quadrants 3 and 4 represent similar operations but with negative voltage polarity, so enabling a reverse direction operation. This flexibility is especially important in motor drive applications where regenerative braking allows the motor to return energy back to the electrical supply during deceleration. improving system efficiency and energy conservation. So the slide also introduces commutation failure, which is a serious problem in control converters. Commutation failure occurs when thyristor does not turn off properly during the commutation process, potentially causing short circuit conditions. So this issue is commonly triggered by voltage sags, disturbances in the AC supply, or improper commutation conditions, and it can significantly affect the reliability and safety of power electronic systems. So this slide explains the issue of harmonics in control power converters and presents common techniques used for harmonic reduction. Control rectifiers draw non-sinusoidal currents from the AC supply because the switching action of thyristors distorts the input current waveform. The use of firing angle control, although useful for regulating the output voltage, can further increase harmonic distortion, especially low order harmonics that negatively affect power quality, system efficiency, and electrical equipment performance. So these harmonics may cause overheating, increase losses, voltage distortion, and interference with sensitive devices connected to the power system. To reduce these undesirable effects, several harmonic mitigation methods are used. As I told you before, passive filters employ introduces and capacitors turn to specific harmonic frequencies to observe and suppress harmonic currents. Active power filters use advanced power electronic circuits to inject compensating currents into the system, effectively canceling harmonic components and improving waveform quality. Another important technique is the use of multi-pulse converters, where multiple converter units operate together through phase shifting transformers to produce a more sinusoidal input current. For example, a 12-pulse converter generates significantly lower harmonic distortion compared to a conventional 6-pulse converter. These mitigation techniques are essential for improving power quality and ensuring reliable operation of modern electrical power systems. So this slide focuses on the crucial topic of harmonics in power electronics, especially specifically their origin in control converters and the various techniques used to mitigate them. Harmonics are a major power quality issue caused by nonlinear loads like power converters. Unlike a simple resistor, these converters don't draw current in a smooth sinusoidal waveform from the AC supply. So instead, they draw current in short, sharp pulse. So this is due to the switching action of the thyristors or SCR. So these current pulses are rich in high frequency components known as harmonics, which can cause serious problems for the power grid, such as voltage distortion, equipment overheating, and reduction in overall power efficiency. So the slide notes that the firing angle control, a key feature of control converters, can actually worsen the harmonic content. So to compact this problem, three primary mitigation methods are used. The most traditional approach is passive filters, which are simple circuits with inductors and capacitors turned to observe specific harmonic frequencies. So a more advanced method is active power filters, which use power electronic circuits to generate a compensating current that cancel out the unwanted harmonic currents. So finally, for high power applications, multi-pulse converters are a very effective solution. This technique uses multiple converters and a phase shifting transformer to strategically cancel out the dominate low order harmonics, resulting in a cleaner input current waveform. This is why a 12 pulse converter, for example, is preferred over a 6 pulse converter in many industrial applications. Okay, this slide covers two advanced concepts critical to understanding the performance and limitations of fully controlled converters. First, for a quadrant operation is unique and powerful capability of fully controlled rectifiers. It allows them to control not only the magnitude but also the directional power flow, making them ideal for applications that require dynamic control of both voltage and current. These four operational modes are defined by the sign of the output voltage and current on a VI plan. Quadrant 1 is the standard rectification mode where both voltage and current are positive, and power flows from the AC source to the DC load. Quadrant 2 is the first inversion mode where voltage is positive but current is negative, so power flows from the DC load back to the AC source. This is essential for applications like regenerative braking and electric motors, where the motors acts as a generator, returning kinetic energy to the power supply. Quadrant 3 is rectification with negative polarity, where both voltage and current are negative. Finally, quadrant 4 is the second inversion mode with negative voltage and positive current, again turning power from the DC load to the AC source. So this comprehensive control makes these converters the backbone of high performance motor drives. We have a commutation failure is a serious and critical issue that can occur in SCR-based converters, especially during the inversion process. It happens when a thyristor or SCR fails to turn off at the correct time, allowing it to continue conducting when the next SCR in the sequence turns on. So this creates a direct short circuit between the two phases of the AC source, leading to a large fault current that can damage the converter and disrupt the entire system. The primary cause of this failure is momentary losses of the reverse bias voltage required to turn off the thyristor, which is often triggered by voltage sags or other disturbances on the power grid. A robust design must account for the possibility of commutation failure and include protection schemes to prevent catastrophic damage. So this risk is a significant consideration in the design and operation of systems like HVDC links that rely heavily on control converters for power transformers. Okay, non-isolated DC to DC converters are fundamental electronic circuits used to efficiently change DC voltage from one level to another without using a transformer for isolation. The primary types are the buck boost or buck boost and Coke converters. They are highly efficient and compact, making them suitable for a vast range of applications. The buck converter is a step-down converter. Its core function is to produce a DC output voltage that is always lower than the DC input voltage. It achieves this by using a switch to chop the input voltage and low pass filter and an inductor and a capacitor to smooth the chop voltage into a steady DC output. This type of converter is widely used in applications like point of load power supplies in digital circuits and LED drives, where lower regulated voltage is needed from the higher source. So conversely, the boost converter is a step-up converter. It takes a DC input and produces a higher DC output voltage. The boost converter stores energy in an inductor during the switch on time and then transfer this energy along with the input energy to the output capacitor during the off time. This capability makes it ideal for systems where high voltage is required from a low voltage source, such as in photovoltaic or solar systems, to step up the panel voltage, or in electric vehicles to provide a high voltage for the motor drive from a battery pack. The buck boost converter combines the functions of both the buck and boost converters, enabling it to either step up or step down the input voltage. A key characteristic is that its output polarity is inverted with specific to the inverter. This versatility makes it suitable for applications where the input voltage may fluctuate above and below the desired output voltage. Similarly, the Cook converter can also step up or step down the voltage, but it transfers energy using a capacitor, resulting in a continuous input and output current, which can be advantages in certain applications. So we have isolated DC converters, are class of power converters that use a high frequency transformer to provide galvanic isolation between the input and output stages. This isolation is crucial for safety, protecting the user and sensitive electronics from high voltages on the primary side. It also allows for the easy generation of multiple different voltage outputs. The flyback converter is a simple and widely used isolated topology. Its operation is based on the principle of energy storage during the switch's on time. Energy is stored in the transformer's core and no energy is transferred to the load. When the switch turns off, the stored energy is then released and transferred to the secondary side to power the load. So this makes it ideal for low power applications like phone chargers and small power adapters due to its simplicity and low component count. So, and the forward converter, in contrast, transfers energy directly from the input to the output through the transformer when the switch is on. To prevent core saturation, demagnetization winding is typically used to reset the core when the switch is off. So the forward converter is generally more efficient than the flyback and is used in medium power applications like computer power supplies. For high power applications, the full bridge converter is a popular choice. It uses four switches to drive the primary winding of the transformer with an AC square wave, allowing for efficient use of the transformer's core in both directions. This configuration is highly efficient and capable of handling high power levels, making it suitable for industrial power supplies and other high power systems. So this slide, before going to a break, I want to finish this slide. So this slide focus on advanced switching techniques that address a major limitation of traditional or hard switching converters: high switching losses. In hard switching, the power semiconductor devices like MOSFET and IGBT turn on and off while both high voltage and high current are present across them. This simultaneous overlap of voltage and current leads to significant energy dissipation during a switching cycle. So these losses increases proportionally with the switching frequency, which severely limits the converter's operating speed and overall efficiency. The dissipated energy manifests as heat, requiring bulky and expensive heat sinks and cooling systems. Additionally, the rapid changes in voltage and current during hard switching generate high level of electromagnetic interference or EMI, which can disrupt nearby electronic circuits. To overcome these issues, you need to have develop soft switching techniques, especially specifically zero voltage switching or ZVC and zero current switching ZCS. The primary objective of ZVS is to ensure that the voltage across the switch is zero and close to zero at the moment it turns on. This is achieved by using resonance circuits to shape the voltage waveform, allowing the switch to turn on with virtually no voltage across it. So this technique drastically reduces the turn on switching losses. Conversely, ZCS aims to have the current through the switch be zero or near zero when it turns off. So by momentarily redirecting the current, the switch can be turned off without dissipating the energy associated with the current voltage overlap. Both ZVS and ZCS are critical for improving the efficiency of converters, especially in high frequency applications where switching losses would otherwise dominate. By minimizing these losses, soft switching techniques enable smaller and lighter power converters with higher efficiency and lower EMI, which is essential for modern applications like data centers, renewable energy systems, and electric vehicles. Okay, I'm going to explain the fundamental concept of DC to DC converters. Let me just 10 minutes off or 5 minutes off. I think 10 minutes is okay. Mr. Um, let me, okay. Um, do you have my, are you hearing me, right? Mr. Al Harbi, are you here? Do you have my voice? Okay, okay, let me have just 2 minutes off. Okay, let me keep continue my lecture. Okay, my discussion will focus on the most common non-isolated topologies, starting with the basic principles of switching converter. I will then provide detailed explanation of the buck step-down converter, or the boost step-up converter, and the buck boost converter. For each, I will describe the circuit, its operation, and its practical applications. Okay, the goal is to provide a comprehensive understanding of how these converters change DC voltage levels, covering both the theoretical concepts and the specific operation of each type. I will supplement the theoretical explanations with an analysis of the key design formulas to help you understand the relationship between the voltage, current, and component values in these circuits. Okay, this slide present the fundamental concept of a basic switching converter as an efficient alternative to linear regulators. In this circuit, the transistor operates as an electronic switch, toggling between fully on and fully off states. which significantly reduces power losses and improves efficiency. The left-hand figure illustrate the circuit. In part A, we see the practical implementation of a DC-DC converter with a transistor and load, while in part B, that is simplified into an idle switch representation to make the analysis clear. When the switch is closed, the input voltage is directly applied to the load. When it is open, the output voltage drops to zero. The waveform shown in part C represent the output voltage over time. It is a rectangular pulse that alternates between the input voltage level and zero, depending on the switching state. The duration for which the switch remains on is denoted as dt, while the off duration is 1 minus d times t, where t is the total switching period. The equations in this slide describe the average or DC value of the output voltage by integrating the output voltage over one switching period and dividing by t. We obtain the average output voltage. V0 is equal to Vs divided by Vs times d. This clearly shows that the output voltage is directly proportional to both the input voltage and duty cycle D. The duty cycle itself is defined as the ratio of the on time to the total period. So D is equal to, this is a duty cycle, is equal to T on divided by total time, which can also be expressed in terms of switching frequency. So therefore, by adjusting the duty cycle, we can precisely control of the output voltage, which is the key operating principle of switching converters in power electronics. The buck converter is a type of DC to DC switching converter that reduces or steps down the input voltage to a lower output voltage. It is widely used in power supplies for electronics. Let me start with circuit distribution. The circuit shown in figure 6.3a is based on the basic switching converter but with an LC low pass filter added. Inductor L smooths the current and stores or release energy. Capacitor C filters the voltage ripple, providing nearly constant DC output, and diode D provides a pass for the inductor current when the switch is off. So it conducts only when the switch is open, or freewheeling diode. We call a freewheeling diode. So switch or transistor turns on and off rapidly, controlling how much of the input energy is delivered to the load. So, and this circuit is called a buck converter or step down converter because VO is less than VS. So let's talk about the operating principles. When the switch is closed or on, the source voltage Vs is supplied to the inductor, and the inductor current increases and delivers energy to both the load and the capacitor. When the switch is open or off, the diode becomes a forward bias and the inductor current continues to follow, cannot change suddenly, supplying energy to load through the diode. Therefore, the inductor ensures a continuous current delivery even when the switch is off. So in steady state operation, after transients die out, the buck converter has these properties. Inductor current is periodic. It means that IL T plus T is equal to IL T. The inductor current waveform repeats every switching cycle. Average inductor voltage is zero, so VL is equal to zero. This follows from the principle of inductor volt second balance, and average capacitor current is 0. This means that over one switching cycle, the, the capacitor does not accumulate charge. So, and for an idle converter, PS is equal to PO. The input power equals the output power. For a non-idle converter, real devices, PS is equal to PO plus losses. The source must supply not only the load power but also the switching and conduction losses. So the buck converter efficiently reduces the input voltage to a lower regulated DC output. The switching duty cycle, or D, determines the average output voltage, and VO is equal to dVs. The inductor and capacitor smooths the voltage and current, ensuring a stable output. Power is conserved apart from losses, making this circuit highly efficient compared to linear regulators. So in summary, the buck converter is the foundation of modern DC power supply, used in everything from phone chargers to computer power systems, because it provides efficient step-down voltage conversions. Okay, this slide continues the study of the buck converter by applying simplifying assumptions and analyzing the switch on interval. So to make the analysis easier, the following assumptions are made. Steady state uh, operation. The circuit is in steady state, so all voltages and currents repeat every switching period. The inductor current never falls to zero. It's stayed positive. This is called continuous conduction mode, or CCM. And the capacitor is assumed to be very large, so that the output voltage V out remains essentially constant. Later, the effect of a finite capacitor will be considered. And the total switching period is T. The switch is on for time dt and off for time 1 minus d times t. No losses in the switch, diode, inductor, or capacitor. When the switch is on, the diode is inverse bias and does not conduct. The source voltage Vs is supplied across the inductor and the load, and the voltage across the inductor is equal to VL is equal to Vs minus V0. From the inductor voltage equation, VL is equal to L di dt. So over on time dt, delta IL is equal to this equation, Vs minus Vo over L times dt. So this represents the increase in inductor current during the on interval. And when the switch is on, VL is equal to Vs minus Vo, positive sequence, and when the switch is off, VL is equal to minus VO, or in negative. So the waveform alternates between positive and negative voltages with zero average in steady state. You can see here, this is zero average. The current rises linearly during on time because VL is bigger than zero, and the current falls linearly during off time because VL is less than zero. The ripple is a triangle with amplitude delta IL, and the average current corresponds to the load current. The the capacitor the capacitor supplies the load during the off time. ISC is the difference between the inductor current and the load current. The waveform is triangle, alternating between positive and negative values. And the inductor current ripple is determined by the voltage differences, Vs minus Vo, the inductor value L, the duty cycle D, and the switching period T. The average output voltage is still Vo is equal to dVs, but now we also know how to calculate the ripple current and understand the detailed waveforms of the inductor and capacitors. In summary, this slide introduces the practical waveform behavior of the buck converter. The inductor voltage alternates between positive and negative values. The inductor current is triangular, always staying above zero in continuous conduction mode. The capacitor current alternates to maintain a nearly constant output voltage. This analysis forms the basic for designing inductors and capacitors in real buck converters. Okay, this slide presents the analysis for a buck converter, which is a step-down converter that produces a DC output voltage lower than the DC input voltage. The core of the circuit is an electronic switch, typically a transistor, which is turned on and off rapidly. When the switch is open, the diode becomes forward bias, allowing the inductor current to continue following to the load and the output capacitors. So the rest of analysis I already talked to you. Similarly to buck converter, the analysis uses the principle of inductor voltage second balance. This principle states that for a converter operating in a steady state, the average voltage across the inductor over one complete switching cycle is zero. This means the voltage time product when the switch is closed must equal the voltage time product when the switch is open. The slide shows the voltage across the inductor when the switch is open is VL is equal to minus VO. This leads to the fundamental relationship between the input voltage Vs and the output voltage Vo and the duty cycle D. The final equation derived is Vo is equal to dVs. This formula shows that the output voltage is a simple function of the input voltage and the duty cycle, which is the fraction of time the switch is on. Since the duty cycle is always less than 1, as the switch must turn off, the output voltage is always less than the input voltage, which is why it's called a step-down converter. The accompanying diagrams illustrate the voltage waveforms and the inductor and capacitor currents, which are crucial for understanding the operation and for designing the converter's components. Okay, this slide explains the operation of a buck step-down converter, which is a type of DC to DC converter used to reduce the input voltage to a lower output voltage. The main focus here is on the current through the inductor, because in a buck converter, the inductor plays a key role in storing and transferring energy. At the top, the equation IL is equal to IR is equal to VO over R shows that in steady state, the average inductor current must equal the load current, since the average current through the capacitor is zero. Next, the maximum and minimum values of the inductor current are derived. These values depend on the average current and the ripple current delta IL, which is caused by the switching operation. These equations, these two equations shows how to calculate I max and I mean in terms of output voltage VO, the duty cycle D, the inductance L, the load resistance R, and the switching frequency F. So this equation 6.13 shows the condition for the boundary between continuous condition mode or CCM and discontinuous condition mode or DCM. So in continuous condition, the inductor current never falls to zero, while in discontinuous condition it does. So the equation gives the minimum inductance required for continuous condition, and equation 6.14 summarize this as L mean is equal to 1 minus D times R over 2F. So in practice, designer chooses L larger than this minimum value to ensure the converter stays in continuous condition. These figures on the right illustrate the converter waveform. So figure A shows the inductor voltage waveform, which alternates between Vi minus Vo when the switch is on, and minus Vo when the switch is off. Figure B shows the inductor current, which rises linearly during the on time. Slope depends on Vi minus Vo over L, and falls linearly during the off time. Slope depends on V minus Vo over L. So the triangle shape reflects the charging and discharging of the inductor. Figure C shows the capacitor current, which is the difference between the inductor current and the load current. Since the capacitor only supplies or observed ripple current, its average value is zero. In overall, this slide gives you the mathematical and graphical understanding of how current behaves in a buck converter, how to calculate current limits, and how to determine the conditions for continuous condition modes. This slide continues the explanation of the Bach converter and focuses on the design of the inductor and the power balance of the circuit. At the beginning, it explains that it designing a Bach converter, one important factor is the peak-to-peak variation of the inductor current, the ripple current, delta I. So shows how this current ripple can be calculated by combining the inductor voltage equation with the switching time. The result is that the ripple depends on the output voltage Vo, the duty cycle D, and inductors L, and the switching frequency F. So this figure, these equations represent rearranges this formula to calculate the required inductance L for a given inductor ripple. So this is useful for design purposes. If the maximum allowable ripple current is specified, the equation tells us the minimum inductance needed to satisfy that condition. Next, this slide emphasizes power balance. Since the converter is assumed to be idle, no losses, the input power equals the output power, and equation 617 shows this equality. PS is equal to PO, VS IS is equal to VO IO. From this, we see that the voltage ratio is the same as the duty cycle. Duty cycle is VO over VS is equal to D, and the current ratio is the inverse. IS is over IO is equal to D. So this relationship is similar to the voltage current transformation of an AC transformer, which is why a buck converter is often compared to the DC transformer. So these figures on the right hand side are the same as the previous slide and help illustrate converter operation. So I already discussed about these figures. Okay, this slide explains the concept of output voltage ripple in a Buck step-down converter and highlight the important role of the output capacitor in reducing voltage fluctuations. At the beginning, it is noted that in earlier analysis, the capacitor was assumed to be very large, which allowed the output voltage to be considered constant. However, in practical applications, capacitors have finite values, and as a result, the output voltage is not perfectly constant. Instead, it exhibits a small variation known as a voltage ripple. The capacitor current is defined as IC is equal to IL minus IR, as shown in this figure. When this current is positive, the capacitor is charging and storing energy. When it is negative, the capacitor is discharging and supplying energy to the load. This continuous process of charging and discharging causes the output voltage to fluctuate slightly around its average value. Using the basic capacitor relationship, Q is equal to CV, any change in charge, delta Q, result in a corresponding change in voltage. Therefore, the voltage ripple can be expressed as the delta VO is equal to delta Q over C. The change in charge is obtained from the triangle area under capacitor current waveform, leading to the expression. So we have this expression, delta VO is equal to T delta IL over HC. So where delta IL is the peak-to-peak inductor current ripple, T is the switching period, and C is the output capacitance. For design purposes, this equation can be rearranged to determine the required capacitor value for a specific ripple level. So this, as you can see in this equation, this shows that the required capacitance depends on the duty cycle D, inductance L, switching frequency F, and the allowable voltage ripple delta V0. So these figures also further clarify this concept, and in this figure, the capacitor current is shown as a triangle waveform with positive and negative regions representing charging and discharging. So in this figure, the output voltage ripple appears as a small oscillation around the DC voltage. This is DC output voltage. In summary, this slide demonstrates how the output capacitor smooths the output voltage by observing the ripple caused by the inductor current, and it provides key design equations to select an appropriate capacitor value based on the desired ripple performance. Okay, this slide presents a clear and structured analysis of a buck converter, one of the most fundamental types of DC to DC converters. It uses a practical example to demonstrate how key performance parameters can be calculated from given circuit conditions. The specific parameters include an input voltage Vs 50 volt and other. We have other information here. So the first step is to determine the DC output voltage. For an ideal buck converter, the output voltage is directly proportional to the input voltage and the duty cycle. So given by the simple relationship, VO is equal to VSD. Substituting the given values, we can obtain the VO. This confirms the step-down nature of the buck converter and highlights one of its key design principles. Next, this slide calculates the inductor current characteristics assuming continuous condition mode CCM. The average inductor current is equal to the load current, which is I out is equal to VO over R, which is equal to 1 amp. And the inductor current is not constant but has a triangular ripple. By calculating this ripple, the maximum and minimum inductor currents are obtained by adding and substituting half of the ripple from the average value. The result are I max is equal to 1.75 amp and I mean is equal to this value 0.25. Since the minimum current remains positive, so this confirms that the converter is indeed operating in CCM. So finally, the slide evaluates the output voltage ripple delta VO, which represents the small variation in output voltage due to the charging and discharging of the capacitor. Using the appropriate ripple formula, the calculated value is approximately delta VO is equal to 4.69 millivolt, which is very small compared to the DC output voltage. This justifies the common assumption of nearly constant output voltage. The accompanying figures help visualize this result. So the inductor current waveform is shown as a triangle shape oscillating around its average value, while the output voltage waveform exhibits a very small ripple around the DC level. Overall, this slide effectively demonstrates how theoretical formulas are applied in practice to analyze and design a buck converter. Okay, this slide presents a complete and practical design example of a buck converter. The objective is to design a converter that delivers a regulated 18-volt DC output to a 10 ohm load while maintaining the output voltage ripple within 0.5% and operating from a 48-volt DC input. The design process includes determining the duty cycle, selecting an appropriate switching frequency, and sizing the inductor and capacitor with suitable ratings. The first step is to calculate the duty ratio, D, for continuous condition mode. Using the fundamental buck converter relationship, VO is equal to VSD. The duty cycle is obtained as D is equal to 37.5%. So this defines the required switching ratio to achieve the desired output voltage. Next, the switching frequency and inductance are selected. A switching frequency of 40 kilohertz is chosen, which is sufficiently high to avoid audible noise and allows for practical component sizing. Based on CCM requirements, the minimum inductance is calculated as 78 microhenry to ensure reliable continuous current operation and provide a safety margin. The inductance is increased by 25%, resulting in a selected value of 97.5 microhenry. The inductor current characteristics are then evaluated to determine component ratings. The average inductor current is equal to the load current calculated as IO is equal to VO over R. The inductor current ripple is found to be delta IL is equal to 2.88 amp, leading to a maximum current of I maximum is equal to 3.24 amp, and a minimum current of I minimum is equal to 0.36 amp. Since the minimum current remains positive, CCM operation is confirmed. Finally, the output capacitor is designed to meet the ripple constraint. A maximum ripple of 0.5% corresponds to delta VO is equal to 0.09 volt. Based on this requirement, the necessary capacitance is calculated to be approximately 100 microfarad, as you can see here. So this slide also highlights important component ratings, including the peak voltage stress on the switch, 30 volt, and the diode, 48 volt, as well as the RMS current requirements. Overall, this slide provides a clear step-by-step design methodology showing how theoretical equations are applied to obtain a complete and practical buck converter design that satisfy given performance constraints. Okay, the boost converter is a type of DC to DC converter that produces an output voltage that is greater than the input voltage. The slide breaks down the analysis by examining the sequence operation in two key intervals: when the switch is closed and when it's open. When the switch is closed for a time dt, the input voltage Vs is applied across the inductor. The inductor stores energy during this time, and the diode becomes reverse bias, isolating the output capacitor and the load from the input. The voltage across the inductor is VL is equal to Vs. The inductor current increases linearly when the switch is open. For the remaining time, 1 minus dt, the energy stored in the inductor is released. The inductor voltage reverse polarity, and the inductor acts as a source in series with the input voltage. This combined voltage Vs plus VL is applied to the output, charging the capacitor and supplying the load. The voltage across the inductor during this phase is equal, VL is equal to Vs minus Vo. So the analyze relies on the principle of inductor voltage second balance, which state that for a converter in steady state operation, the average voltage across the inductor or over one complex switching cycle is zero. By applying this principle, the fundamental relationship between the input and output voltages for a boost converter can be derived. So VO is equal to 1 minus D times Vs. Since the duty cycle D is between 0 and 1, the output voltage VO is always greater than the input voltage Vs. So the waveforms on the slide visually represent the inductor voltage and current over switching cycles. Okay, this slide present a clear and systematic analysis of converters operation under ideal conditions, assuming a steady state behavior and a sufficiently large output capacitor to maintain a nearly constant output voltage. The operation is explained by dividing the switching period into two key intervals based on the state of the switch. In the first interval, when the switch is closed for a duration of duty, the input voltage Vs is applied directly across the inductor according to Kirchhoff voltage law. The inductor voltage is VL is equal to Vs. During this time, the inductor stores energy and its current increases linearly. The rate of increase is given by DIL over dt is equal to Vs over L, which indicates that the slope of the inductor current depends on the input voltage and inductance. In the second interval, when the switch is open for the remaining time, 1 minus d times t, the inductor current must continue following. As a result, the diode becomes forward bias, providing a path for the current. In this state, the inductor releases its stored energy and effectively act as a voltage source. The inductor voltage becomes VL is equal to Vs minus Vo. So which is negative since Vo is bigger than Vs. Consequently, the inductor current decreases linearly with a slope given by DIL is over dt is equal to Vs minus Vo over L. A key principle used in this analysis is the inductor volt second balance, which states that the average voltage across the inductor over one complex switching cycle must be zero in a steady state. By equating the volt second products of the two intervals, we obtain the fundamental relationship for the boost converter. VO is equal to Vs over 1 minus d. So this equation clearly shows that since the duty cycle d is always less than 1, the output voltage is always greater than the input voltage, confirming the step up nature of the boost converter. The waveforms included in the slide further illustrate this behavior. This slide explains the key steady state analysis of the boost converter using the inductor volt second balance in principle. In steady state, the inductor current must return to the same value after each switching cycle, which implies that the net inductor voltage over one period is zero. During the switch on interval, the inductor is connected to the input source and its voltage is Vs. During the off interval, the inductor transfers energy to the load and its voltage becomes Vs minus Vo. Applying the volt second balance, we will have these equations. So this result clearly shows that the output voltage is always higher than the input voltage, since the D is equal to D is should be between the 0 and 1. So using the voltage gain relationship and simplifying, the average inductor input current can be expressed in terms of Vs. So we can have these equations. Okay, this slide continues the analysis of the boost step up converter and focus on determining the maximum minimum inductor currents and the minimum required inductor size for continuous operation. So it then derives an expression for the average inductor current. The slide begins by starting that for a steady state operation, the net change in inductor current over one cycle must be zero. So this principle is used to derive the expression of for the minimum inductor current. I mean here. So I mean we have I mean here and maximum inductor current I max. The formulas provided shows that these values are determined by the average inductor current IL and the current ripple delta IL. So this slide then present the formula for the minimum combination of inductance and switching frequency required for continuous current in the boost converter. This is a critical design parameter as an inductor value below this minimum will cause the converter to operate in discontinuous condition mode, DCM, which changes the converter's voltage relationship. From a design perspective, the slide also provides a useful relationship for expressing the inductor value L in terms of the desired current ripple, delta IL. This allows designer to select a suitable inductor based on their specific ripple requirements. The final equations confirm that the average inductor current can be expressed in terms of the input and output voltages and the load resistance. The the waveforms visually illustrate the minimum and maximum inductor currents and the triangle shape of the current ripple. Okay, this slide extends the analysis of the boost converter by examining the output voltage ripple, which is an important non-ideal effect in practical power electronic systems. Although the ideal output voltage of a boost converter is constant, in reality, it contains a small fluctuation called ripple. This ripple is mainly caused by the periodic charging and discharging of the output capacitor during the switching cycle. To quantify this, the slide analyze the capacitor charge variation using the basic relationship. So we will have delta Q is equal to C delta V. This is a Faraday law. By studying the capacitor current waveform over one switching period and integrating the charge variation, the peak-to-peak output voltage ripple can be derived. The final expressions shows that the ripple depends on the load resistance R, switching frequency F, duty cycle D, and input-output voltage levels. The ripple can be expressed in equivalent forms such as delta V0 is equal to these equations. So this equation illustrating that increasing capacitance or switching frequency reduces ripple, while higher load resistance or duty cycle increases it. So, and this slide also provides a design-oriented rearrangement to determine the required capacitor value for a specific ripple value. So by using of this equation, we can find the required capacitors. Okay, this slide present a complete step-by-step design example of a boost converter moving from a specification to component selection. So the design goal is to convert the 12-volt DC input into a 30-volt DC output across a 50-ohm load while maintaining continuous inductor current and keeping the output voltage ripple below 1%. The first step is determining the duty cycle using the boost converter voltage gain relationship. So VO is equal to Vs over 1 minus D, solving for D. D is equal to, so can be is equal to 1 minus Vs over Vo. So this indicates that the switch remains on for 60%. So 0.6 representing 60% of each switching period. So next, The inductor is designed to ensure continuous condition mode using the selected switching frequency of 25 kilohertz. The minimum inductance required is calculated, resulting in L minimum is equal to 96 microhenry. To ensure safe continuous continuation mode operation under variations, a high standard value of 120 microhenry can be selected. So the average inductor current is then obtained using power balance between input and output. PO is equal to P output, which gives the IL is equal to 1.5 amp. From this, the peak and minimum inductor currents are equal to 2.7 amp and 0.7 amp. So since the minimum current is still positive, the converter indeed operates in continuous condition mode, validating the design assumption. Finally, the output capacitor is sized based on the allowed ripple with a maximum ripple specification of 1% of 30 volt. Delta VO is equal to 0.3 volt. Using the ripple expression, the minimum required capacitance is C min is equal to should be 48 microhenry. Overall, the slide demonstrates how duty cycle inductor and capacitor values are systematically chosen to meet voltage conversion, current continuity, and ripple constraints in practical boost converter design. This slide presents a comprehensive boost converter design example. The goal is to design a converter that provides a stable 8-volt output to a 1 amp load with a input voltage varying between 2.7 volt and 4.2 volt. This design must meet specific requirements for inductor current variation not exceeding 40% of the average current and output voltage ripple not more than 2%. The solution begins by analyzing the worst case conditions for the design, which are at the two extremes of the input voltage range. The switching frequency is arbitrarily chosen to be 200 kilohertz. The duty ratio D and average inductor current IL are calculated for both the 2.7 volt and 4.2 volt input voltages, as these values determine the inductance requirements. The variation in the inductor current and the minimum required inductor size for continuous operation are then calculated for both input voltage cases. The design must satisfy the requirements for the entire input voltage range, so the larger of the two inductor values is selected. The slide shows that an inductor of 13.1 microhenry is sufficient to meet the specifications. Finally, the required capacitance is determined based on the output voltage ripple constraint. The formula for capacitance is used, and the minimum capacitance required is calculated to be 20.7 microfarad. The slide also calculate the peak-to-peak current variation and the voltage ripple due to the capacitor's equivalent series resistance, which is an important practical consideration. Okay, this slide provide an in-depth analysis of the buck boost converter, a versatile DC to DC converter capable of producing an output voltage that can be either higher or lower than the input voltage. The analysis is based on the inductor volt second balance principle and assumes idle steady state operation. The converter operation is divided into two intervals depending on the switch state. When the switch is closed for a duration of duty, the input voltage Vs is applied directly across the inductor, so the inductor voltage is VL is equal to Vs, and the inductor current increases linearly, while the diode is reverse bias and isolated the output during this interval. The change in inductor current is delta IL on is equal to Vs over LDT. When the switch is open for the remaining interval 1 minus dt, the inductor current must continue following, forcing the diode to conduct and deliver energy to the output, in the case of inductor voltage. Okay, the buck boost converter is a versatile DC to DC converter that can generate an output voltage either higher or lower than the input voltage depending on the duty cycle. The key A key characteristic of this converter is that the output voltage polarity is opposite to the input voltage. The analysis is based on the inductor volt second balance principle under steady state operation, which states that the average voltage across the inductor over one switching period is zero. The operation is divided into two intervals. When the switch is closed for a duration dt, the input voltage Vs is applied across the inductor, so VL is equal to Vs. The inductor stores energy and its current increases linearly when the switch is open for the remaining interval 1 minus d times t. The inductor current continues to follow through the diode, which becomes forward biased and transfers energy to the load and output capacitor, and in this case VL is equal to minus VO. Applying the volt-second balance condition leads to the fundamental voltage conversion ratio. VO is equal to minus D over 1 minus D Vs, showing that the magnitude of the output voltage depends on the duty cycle, where for D less than 0.5, the converter operates in buck mode, step down, and for D is bigger than the 0.5, it operates in boost mode, step up. In addition, the slide drives the average inductor current by using power balance between the source and the load, where the average source current is related to the inductor current through Is is equal to DIL, and this leads to an expression for the average inductor current in terms of the input-output voltages and the load resistance. This slide continues the analysis of a buck boost converter, and focuses on the calculation of output voltage ripple and the minimum inductor size required for continuous condition mode. This slide starts by presenting the formula for the minimum and maximum inductor current. These are derived using the average inductor current and the current ripple, which is crucial for verifying that the converter operates in CCM mode. For CCM mode, the minimum inductor current must be a positive value. The slide then provides a formula for the minimum inductor Lm mean required to ensure continuous operation, which is a key design parameter. If the inductor value is less than Lm mean, the current will drop to zero during each cycle and the converter will operate in discontinuous condition mode. The later half of the slide explains the output voltage ripple. The ripple is the small fluctuation in the DC output voltage and is caused by the charging and discharging of the output capacitor. So the analysis uses the principle of capacitor charge balance to derive a formula for the voltage ripple, or delta VO. The slide also highlights the practical consideration of the capacitor equation equivalent series resistance, or ESR, so which can contribute significantly to the output voltage ripple. These waveforms in the right hand side illustrate the inductor current, diode current, and capacitor current, which are essential for understanding the ripple calculations and the overall operation of the converter. So this slide presents a numerical example for a buck boost converter design, which is a versatile type of DC to DC converter capable of either stepping up or stepping down the input voltage. The problem provides a set of parameters and input voltage Vs of 24 volt, duty cycle D of 0.4, a load resistance R of 5 ohm, and inductance L of 20 microhenry, a capacitance C of 80 microfarad, and a switching frequency F of 100 kilohertz. The goal is to determine the converter key performance matrix, output voltage, inductive currents, and output voltage ripple. The solution begins by calculating the DC output voltage VO. A unique characteristic of the buck boost converter is that the output voltage has a negative polarity relative to the input. Using the formula, VO is equal to minus Vs. Uh, so the output voltage is calculated to be minus 16 volt, you can see here. So since the duty cycle is 40%, is less than the 50%, the magnitude of the output voltage 60 volt is smaller than the input voltage 24 volts. So demonstrating the step down capability. Next, the inductor current is analyzed. So the average inductor current IL is calculated to be 5.33 amp. This is crucial value because the inductor handles the power transfer in the circuit. The slide then determines the inductor current ripple, delta IL, to be 4.8 amp using the average current and the ripple. The maximum and minimum inductor currents are found to be Imax is equal to 7.73 amp and Imin is equal to 2.93 amp. The fact that the minimum current is positive confirms that the converter is operating in continuous condition mode where the inductor current never drops to zero. Finally, the output voltage ripple is calculated, which represents the small fluctuation in the output voltage. The ripple is determined by the capacitance and the ripple in the capacitor current. The slide uses the formula VO, delta VO over VO, to calculate the voltage ripple as a percentage of the output voltage. The result is a ripple of 1%, which is typically a very low value indicating a well-designed output filter. Okay, this exam question focus on the steady state analysis and key performance characteristics of an idle buck converter operating in continuous condition mode. The converter steps down an input voltage of 48 volt to an output voltage of 12 volt, and the first task is to determine the duty cycle using the fundamental book converter relationship. VO is equal to dVn, which directly links the output voltage to the switching control. With a switching frequency of 200 kilohertz and an inductance of 50 microhenry, the problem then moves to evaluating the inductor current waveform, where the average inductor current is equal to the load current of 2 amp under idle conditions. Using the conductor ripple current expression, the peak-to-peak ripple is determined, allowing calculation of maximum minimum inductor currents around the average value, which is essential for verifying CCM mode. So finally, the question examined the effect of the increasing the inductance of 100 microhenry, highlighting that the larger inductance reduces the slope of the inductor current ripple, thereby decreasing the ripple magnitude while keeping the average current unchanged. This part reinforces the fundamental trade-off in converter design between inductance size, current ripple, and dynamic response. First, we determine the duty cycle of D of the idle book converter operating in continuous condition mode using the relationship VO V out is equal to D times Vn. The duty cycle can be found 25%. meaning that the switch is on for 25% of each switching period. Next, we calculate the inductive current ripple and the maximum minimum inductive currents. The average inductive current equals the load current, so IL is equal to I out is equal to 2 amp. The peak-to-peak ripple is given by delta IL is equal to V out times 1 minus D over LFS, which gives 0.9 amp. From this, the maximum and minimum inductive currents can be calculated based on this equation. Since the minimum current remains positive, the converter is confirmed to be operating in CCM mode. Finally, the effect of increasing the inductive value has been considered. Since the ripple is inversely proportional to inductance, delta IL is proportional to 1 over L, doubling the inductance from 50 microhenry to 100 microhenry reduces the ripple by half, so resulting in smoother current and voltage waveforms through the at the expense of increased size and cost. So I want to close my session here. So are you here?